Okay, so we better start this section, this afternoon section. We have as a first speaker, Antonio de Toledo Pisa. I know you by name for a long time, but it's the first time having a chance to see a talk with you. And Antonio is going to talk about the correlated, not so many body, low-lying states of bosonic atoms in low dimensions. Okay, take it away.
Well, thank you very much. Thank you for the opportunity. I have to thank the organizers for giving me the chance of speaking to you for some time here. I'm going to talk about many-body physics in a kind of old-fashioned way, and I would like to convince you that one can use very old-fashioned ideas of many-body physics in order to understand things that are very common now, but from a slightly different point of view. Okay. The talk is kind of divided into two parts. The first part is just to set the stage for the second part, and the second part is just an exercise using some tools developed in the end of the first part. Using these ideas that I was mentioning of old-fashioned many-body physics, originating in nuclear physics, basically, we'll study some smoothed-out phase transitions going from Hubbard to Bloch, and then superfluid fractions and their currents. I mean, I understand this has to do with essentially with the Mott transition, and but from a few body point of view, not statistical mechanics. Then we, for the superfluid fractions, we study some cranking ideas and identify some currents related to the so-called superfluid fractions. And then we turn up these rotations, and they are not, then they become what is called currently gauge fields, and then study the currents under the gauge fields from this point of view of these currents. Okay, so this is the basic plan. I start with the Bose-Hubbard Hamiltonian, which is the simplest thing. And here, this is Hubbard showing his model himself. And this is the physics that is going to be in the next few slides. It's the so-called the Mott transition. It's taken from the famous paper of 1989 by the Fishers and other people. And you have this lobes here. Here you have incompressibility in this mu here, and you have here have occupation n equal 1 per site, n equal 2 per site, n equal 3 per site, and so on. This is the superfluid region, and this is the Mott insulator region. And there are phase transitions here that are discussed in this paper, classified, and so on. Okay. This is the standard thing. I would deal with this in very small systems, in the sense that I have a periodic system with m sites, m being a few, not very many, and I will just take m independent sites, completely independent sites, and I put some particles in, so I just turn off the hopping term of the Bose-Hubbard Hamiltonian. I have only that. And then I compute here, I show here the removal energy or addition energy of an additional particle. Here I have 0 particles. Then as I add up to m particles, m being the number of sites, I can put each one in a different slot, so they don't interact. This is just a local site interaction. And then after that, I get a jump here. So I get a bunch of levels or removal energies here. Then I get a second bunch here, until I get 2m particles and then a third bench and so on. So this is just the no hopping situation. Then I can go further and do a perturbation theory, turn on a small j, and find the slopes of the removal energies or addition energies that stem out of this bunches here, 0, 1, 2, and I get these angular coefficients. I can go to large j's and small u's and do perturbation theory here, and I see that on the far right you expect equally spaced removal energies with a certain slope, and the spacing between them is 1 over m in these units exactly. Okay, so now you do a calculation and you see what you see. You get a bunch of things that start here and interpolate between these two extremes. Here would be the superfluid domain, and here you have the lobes. You see, the lobes are here. So this is a way of understanding the Mott transitions without any phase transition at all. Okay? What is happening here? You have a bunching of levels. The bunching of levels, which is reduced as the J is turning on. The bunching is due to independent sites. As the J is turned on, the sites become less independent. In terms of old-fashioned nuclear physics, this is just a shell effect. Okay, and so you can see these holes here as shell gaps, and then the action of this term here essentially washes out the shell effect, and the superfluid phase is a phase in which there are no shell effects anymore. This, I think, is interesting because it gives you a picture to see those phase domains. And I like this picture because it's a soy plantation. It gives you an idea of how to organize that in your mind. You see, this is a tree which remains in a soy plantation, and this is a Mott insulator there. And these results are quantitatively very good. I mean, this is an actual collection of fancy calculations of the first lobe in one dimension, which is what I'm doing here, taken by the review of Casalila and et al. And you see that the end of the lobe is around 0.3, and the part around 0.3 is the same thing here. So that the thing fits very well. And you have just a few particles here, 5, 10, here 11, 12, and so on. Okay. To see that this is not just a one-dimensional thing, this is a very naive calculation of the Hubbard model itself on a 3x3 array in 2 dimensions with periodic boundary conditions. I have from 1 to 10 particles just to show the first lobe. You see, you say, if you don't believe that lobe, I can show you a picture in which I put the result of a calculation done here by a student of Arnaldo Gamal a few years ago. And this is a Monte Carlo calculation, and it done completely independent of anything. I did this calculation when she told me that she was doing this, and then she gave me the results, and I could plot it here. I mean, no adjustments made. So she had problems with convergence, numerical problems here, and you understand very clearly why if you look at this picture. Here, the transition is different from here. Okay? So that's not I'm going to work with. I want to work with on a more fundamental level, even though it's a model. It's a very effective model. I will deconstruct that Bose-Hubbard model by just having a regular field Hamiltonian, having a one-body part with an array here, periodic array in a circle, and then a two-body interaction term, contact interaction there. This is, of course, an effective two-body force. It is not real force. So this, for instance, this system is supposed to describe bosonic atoms. That is related to the scattering amplitude. And you know very well, and I will deal with the ground states of such systems. Of course, this is a fake ground state because the true ground state is beyond the description by this Hamiltonian. But okay, but anyway, this is a microscopic Hamiltonian in configuration space. Phi is the angle. There is a radius r, and this is a periodic array on the circle. So what I do, I need a good single particle basis. So I diagonalize, I solve the one-body problem. This is a standard thing. You get block functions, okay? So you have, you can express this Hamiltonian, represent this field Hamiltonian in terms of block energies and block functions. The block energies are here, and the A operators create particles in the block functions, okay? This is the block eigenvalue problem. And here I have two-body integrals coming from here, which involve four different block functions. I'm restricting myself to the first band of block states as to make contact with the standard Bose-Hubbard model. So what I do here is to diagonalize H within the states involving just first band orbitals. This is the same thing that we did before, but more microscopically a little bit. And we get the same thing, of course. Here is the transition. These are now the removal energies. Forget about the chemical potential. This is just a removal energy, particle removal energy. It's discrete. And these are the occupation numbers of the one-body density. You can see the trace of the one-body density is here is 5. There are 5 particles. You have once they start all together when you have very small hopping, and then as this hopping increases, you approach this superfluid phase. There is one state, the Q equals 0 block state that gets all the population, and the others go down to 0. This is for the commensurate things, where you have here 5 particles, and here you have 6 particles, so you have this breaking here. So, see? Even though it's a microscopic model, I'm still parameterizing in terms of J and U for ease of comparison. J corresponds to 1/4 of the width of the first block bands. And U is related to that lambda and the mean value of the two-body integrals. Okay? The next thing I want to talk about is cranking, and now I want to crank this model. Why I want to crank? Crank means turn it around and go to the co-rotating system, okay? Then the array was, when it rotates, it was time-dependent. You make a gauge transformation to eliminate this time dependence, and you get, as a result, this extra term here. Omega is the angular velocity of rotation. The reason to do that is that I can, it's well known, the general result that the ground state energy of this system under these situations can be written in this way. It's the 0 omega, non-rotating eigenvalue plus omega squared term plus terms of the 4th order. So if I rotate it very slowly for very small omega, what I get is something, a straight line in omega square, and which gives me this effective moment of inertia. If I divide this effective moment of inertia by the rigid moment of inertia, I get something I can call the superfluid fraction. Okay? So a way of writing this in terms of the derivatives here is the derivative of E of omega in terms of omega square, the first derivative, or 1 over omega times this derivative at omega equals 0. So it's a limit expression. The interesting thing is that you can get this superfluid fraction also from currents circulating in this system. And it's very easy, elementary, to find the currents. What you do, you have to remind yourself of the Feynman-Hellman relation. You want the derivative of the energy with respect to omega. This is related to the expectation value of the derivative of the Hamiltonian with respect to omega. Now, this is very nice because the derivative of the Hamiltonian with respect to omega is a one-body operator. So these currents are completely determined by the one-body density matrix. You don't need the correlations except to produce some incoherence at the one-body level. Okay, if you have more than one single natural orbital. Okay. If you do this, if you do all the algebra, you say this is a one-body operator, as I just said. I can write the one-body density in this way and write it in terms of occupations and natural orbitals. This is a single sum. And then I can write this moment of inertia as 1 over omega, that's the first factor, and then the integral over phi of a certain current, which can be written very simply in this way. This current here is an incoherent sum of natural orbital contributions with weights given by the occupations, and it has two terms. This is a momentum-dependent thing, the term that is the usual current momentum-dependent term, which involves the derivative with respect to phi. And this is a convective term, sort of. It has to do with the rotation, which comes from the linear term of the Hamiltonian in the momentum, and when you take the derivative. Okay? So I have a current here. I have the currents, and I can calculate these currents from the natural orbitals themselves. Furthermore, there is an interesting thing about this current, is that for stationary state, the continuity equation requires that the density does not change, and this implies that this current is solenoidal. It is divergenceless. So in a one-dimensional circle, it means that it's constant. There's no other way to do it. Okay? Then, if I look at what I need here, I need 1 over omega integral over phi of something, but phi is solenoidal. So when I do this integration, I just get the current anywhere, like in the origin, times 2 pi, which is the integral. And then you see this, the current anywhere times 2 pi over omega, which is an integrated over time, which corresponds to 1 full circle of the rotation. So this is a very obvious interpretation of this expression, right? Note that because of the units I'm using here, this current is a moment of inertia current. It has the dimensions of a moment of inertia, you see? The omega turns it into current. It's not that. Okay, and so this is the result of the superfluid fraction. The naive expectation would be it goes to a very large value, I mean near 1, when the lobe closes. That's not true, okay? It only goes to unity when essentially the barrier disappears. Okay, what happens is that point 3, you remember, is the point where the lobe would close for the... then what happens is there dies the effect of the two-body interaction. This is a weaker and this is a stronger value of the two-body interaction. You see there is a depression here. Stronger two-body repulsion depresses the superfluid fraction inside of the lobes, but they heal soon enough there. So what you see there is not the establishment of a superfluid regime, but the closing, the ending of the effect of the repulsion on the superfluid. You can even do this calculation for an ideal gas, and you see everything heals to the ideal gas around this point here, okay? So these depressions have to do with specifically a two-body force on the, okay? So this is all old stuff. I have more calculations you want. The first lobe is here. Well, it doesn't matter. This is the first lobe. You see that it heals at point 3. You have here several calculations having to do with the commensurate case here, and the incommensurate case, the greens, and here, okay? Actually, there are three curves here. One is barely seen. You have the green and some very tiny, nearly invisible red points here, which means 4 and 6, before and after. The blue one is the 5. And this the same for the second lobe here, okay? Okay, so this is the end of the first part. It was made just to introduce those currents. Because now I take a problem that has been, which came across in the literature, which is in many different contexts. It's just a circle which is rotating with angular velocity omega, in which there is sometimes called a weak link or something. Of course, I can apply all the ideas there except the block functions, but I can, of course, do likewise and have this same Hamiltonian already with the cranking put in. And here I have this barrier, which is represented this way. I use an actual barrier, not a delta barrier. It could be a delta barrier, but it's this is actually a cosine square. This is kind of, cosine square is nice because it has a zero derivative here, so it's the derivative continues, and I choose the width here. This is the function f of phi, and the barrier is u naught f of phi. So this is just pushes this up and down. U0 is the top value of the barrier here. Okay. Okay. I want to look at the current in the ground state as a function of omega now. Now I'm not doing just the superfluid fraction, because that all the Feynman-Hellman tricks and so on work for any omega. Okay, it doesn't not. And so I adapt and use and diagonalize H within states involving a set of cranked ring orbitals. For each different value of omega, you can find new wave functions and do a diagonalization there, okay? There are several parameters, so it's sometimes awkward to show the results because I can vary the barrier height, I can vary the cranking angular velocity here, and I can, of course, change the two-body effective interaction here, okay? This is the paper which prompted me to deal with this model and to see what these currents do there. Actually, the paper uses just the energy derivative definition of the current. they don't use the natural orbitals. So I use this solenoidal current. I know it's a solenoidal current, so it's a constant. And I can check the calculation using the energy derivative or the current to calculate superfluid fractions with very small omega. And you see dots are from currents, and the line is from energy derivatives. They agree completely. They're the same thing. And now, but then I want to extend the superfluid fractions to higher omega. And then I don't call them superfluid fractions anymore. I call them circulating fractions for reasons that will be clear. Okay? But the definition is exactly the same. 2 pi over omega, that's an effective circulating moment of inertia divided by the rigid moment of inertia. When I say circulating fractions, I mean fractions which are circulating in the co-rotating frame. Okay? If all the matter is dragged around, the circulating fraction is 0. Okay? So here I show the 5 lowest Crankel single particle levels. The effect of a barrier is increasing to the right, a low barrier, a medium barrier, and a high barrier. You see that it induces avoided crossings here and mixes the levels. And there is a periodicity to them. This is just one period. This is periodic with the units I use, the period 2 in omega. Okay? The avoided crossings are due to the angular momentum breaking by the barrier, because at no barrier, of course, you have good angular momentum. And here you don't have a good angular momentum anymore, and you have almost good, and when they get close to each other, they mix. And so this is, here they mix a lot, and here they mix a little bit, okay? Then I can evaluate the current itself, the J, as a function of omega, and it also omega periodic. That's funny, but it's periodic, and they feel, the current feels the avoided crossings. This is calculated, the first period of the current calculated with this barrier and this, with this barrier. You see a rounding there, and there is not only a rounding, but an strong attenuation there. Here there is already an attenuation. I plot all the 3 plots in the same scale so that you can see how it shrinks while it rounds, okay? Okay. I said this is kind of funny because the ingredients which make this current are not periodic. Here they are. Here you have the current calculated at omega equals 0.5 for a certain barrier and a certain two-body interaction. The same here, but here it's one period after what's found here. The green line is the solenoidal current. And it's made of 2, remember there are 2 ingredients. There is a momentum-dependent one, and there is a convective term, and they add to give a constant thing. Here I get the same value. Note that here the scales are not the same. This is 1 and this is 4. So this is also 0.6 something. So it's exactly the same value, but the ingredient is completely different. These are plots of the real and imaginary parts, blue, and imaginary parts dashed, and so on. And the brown ones are the first, second, more occupied natural orbital for this case, and these are the natural orbitals for that case. So it's funny that you get the same horizontal green line for widely different from apparently very different ingredients. But it's easy to look at the model a little more closely and to find out that the single particle wave functions and the natural orbitals, which is fun, interesting, the omega periods apart, they are very simply related, and the related is simple. If I take some eigenfunction at angular velocity omega, I can go to the eigenfunction at angular velocity omega plus 2n, n is integer, by just multiplying that by e to the 2n phi. This relationship does not change the two-body matrix elements that go into the Hamiltonian, the many-body Hamiltonian to be diagonalized. So numerically, the Hamiltonian will be the same. So that numerically also the result of the diagonalization is the same as you got before, except that they refer to modified orbitals like that. And when you calculate, so when you diagonalize that, the one-body density, you get that the natural orbitals are also related in that way. And that is sufficient to show the difference between this graph and this graph. What happens is that the brown here gets an addition from the up here, and this gets an addition down, and they cancel exactly, which come from this additional term here. So it's kind of trivial, the fact that the thing is periodic, okay? Now I will compare currents with circulating fractions. You remember that circulating fractions have the difference because they have an extra omega in the denominator. They reduce to the superfluid fraction when you get very small angular velocity here. So the blue here means, for these parameters, means the circulating fraction. It starts with 1 here for this high barrier and for a strong lambda. And this is the current. It's always periodic. And this is the current divided by omega and some other things, and which is damped because of the omega factor here, okay? So, and you see the superfluid fraction thing is very stable in the beginning here. Here is interesting because it's a very weak two-body force with the same barrier parameters. You see that you see much more, here the effect of the avoided crossing is quenched by the strong two-body force, and here you see the rounding very clearly, and also the rounding here on the circulating fraction, but you see still you get stability there. But there is some depletion also of the superfluid fraction there. Okay. It means that the current goes the other way. Okay? You see the negative thing here means the current is negative, and the current is negative because it goes the other way. Because of the level crossing. You see, all the current has to do with irregularities during one period. Because what happens next is just a reproduction of the same irregularities with multiplying by some e to the I n phi, okay? So this imbalance, this is the level crossing. The level crossing causes an abrupt change of the avoided crossing smoothens that out. So here this is superfluid fraction. Okay. But you see, then there is a very visible effect of the strength of the interaction. to reduce the effect of the level crossing induced by the barrier, avoided crossing induced by the barrier. You can see that also by studying the circulating fraction as a function of the barrier height from very low to very high barriers with 2 lambdas. The first value corresponds to the blue curve. You see that for the very small, the circulating fraction drops very quickly. And here it starts with a horizontal derivative. And this, on the other side, where the circulating fraction is negative, you see it turns around. Okay. This is another way of showing it. Here I have as a function not of the barrier, but of the two-body force parameter, which increases from top to bottom. This is the highest value, and this is the lowest value. At omega equals 0.8, and here omega from top to bottom, yes. Here, very high, you see, you have suppressed circulation. And here is the reverse also. This is the negative. It goes only to 0.7 or so because of the 1 over omega parameter, extra factor that you have there. And this is just trying to show most things together. I have 3-dimensional plots of the circulating fraction and of the current. You see the current is as a function of the two-body force parameter. Here you have the angular velocity during the first period. You can see that there is a very small rounding of that for the weaker things here. This has to do with some very slow downwards trend here. And then this is for a very low barrier. If you go to the higher medium barrier, you can see that there is a transition domain here, which is rather wide. It looks sharp because this is a logarithmic scale. But you see it's more rounded off for the weak interactions, and the strong interactions tend to, okay? And this is a stronger barrier. You have the effect more clearly. Here at the left, for the very slow values of omega, you can see the superfluid fraction. You can read it here. And in the previous one also here. And in the previous one also here. Okay. Okay. So this is what I wanted to show you. It's not much, but it's what I have, okay? I just go to the fine. There is a limitation to all this. For the stronger interactions, it can be detected. I didn't show you, but I can point out to you if you want, where there are clear indications that you need a bigger many-body space. The many-body space has to be increased by adding more orbitals. It's very clear. I took how can I know that? There are indications of this very clear, which are the following. You remember when I used the Feynman-Hellman theorem, you relate the current, the derivative of the energy to the expectation value of the derivative of the Hamiltonian. And then I told you the derivative of Hamiltonian is a one-body operator. This is true if you don't have any truncation. If you do the truncation, I did, for instance, what did I take? I took the lowest 5 levels. But you remember that there are level crossings. If there are level crossings, there are the last level starts with dominating values of one angular momentum and ends with another angular momentum. So there is an omega dependence on the single particle space I'm using. Okay? And since there is so there is an omega dependence on the many-body space I'm using. And the diagonalization I'm doing is not a diagonalization of the Hamiltonian, the full Hamiltonian, but of the projected Hamiltonian on this space. And the projection operator is omega dependent. So when I took the derivative, I had to take an extra derivative of the projection operator part. That effect shows clearly when you compare near the transition region from positive to negative currents of the values you get from the energy derivative directly and from the currents. The currents are insensitive to that because they just leave out these extra effects. But the energy doesn't know that. So he carries the full effect. So, and you can see a discrepancy precisely in the region where you can detect an omega dependence of the space. So you need more, and so it's, but this is a very naively made calculation. It's done on my desk computer with the resources that were there. No effort to improve anything or to optimize anything. So, okay. Thank you.
We have time for questions. Anyone there? Ready? No. Okay, I have a couple. In your methodology,
it's not a methodology,
or in your approach, would you be able to study non-equilibrium dynamics? Meaning, I guess you would need to have the wave function.
No, this is complicated. I think all the things that have been doing, people have been doing in non-equilibrium things and time-dependent things are very, very important. And this is not no competition for that. No.
But essentially, why?
Huh?
Why? Because you don't determine the wave function?
I mean, you can do it the naive way. If I can diagonalize a Hamiltonian and I can believe enough eigenvalues and eigenfunctions, I can try to use the quantum mechanics textbook way of deriving time-dependent results. But that's no, I don't think that's a very efficient way of doing it. But it can be done.
Can be done.
Oh yes, but I don't think it's the strong point of this.
Yeah, and the other thing is that when I see you adding more and more particles to your system, the Hamiltonian, I was just curious whether it has only two-body interactions, or you can have higher order interactions?
No, two-body interactions.
Only two-body interactions?
No, this is a simple model.
Okay.
Two-body interactions which are effective interactions.
Okay.
You see, these are effective interactions which depend on the scattering amplitude, which is on a special case of the scattering amplitude, which is just the scattering length, okay?
Okay.
The scattering length is of all orders in the potential.
So it's like your model described as a ensemble of particles, but they only interact when they're two by two.
This is a standard thing that people use when they do Gross-Pitaevsky stuff.
Yeah. It doesn't have actual higher order interaction.
Yes, and it, of course, it's you have to think about this, but.
How difficult would it be to include?
But you know, there are some funny exact results, like, of course, the Lieb-Zeilinger result, so-called Gross-Pitaevsky limit.
Okay.
It shows that if you take a system which interacts through actual potentials, but purely repulsive potentials to avoid possibility of ground states and other things. So it's really meant to be unbound. Mm-hmm. And if you evaluate the scattering length of that potential, and you construct with it the Gross-Pitaevsky potential, then they show that in the limit where the scattering length goes to 0, such that the number of particles times n is constant, then the minimizer of the Gross-Pitaevsky potential provides for an exact solution of the many-body problem with the potential you started with, not with the effective potential. And so Lieber, I remember he was very incisive in saying that the Gross-Pitaevsky functional is not a mean field functional, because what's there is not the potential, but it's an effective thing which has to do with the, and it's very important to prove the theorem.
Okay.
It's the T matrix.
The T matrix.
It's the T matrix. Yes.
Yeah, I mean, it's not a potential. It cannot be the potential. It's a much higher order thing, which is the T matrix.
Yes. And it's essential that it be the T matrix to prove the theorem.
Yeah.
You see?
That's right. Yeah.
You see, all the many interaction effects are hidden precisely in the fact that you are using the T matrix and not the potential. Okay. So it's very important to realize, to prove this theorem, that it's not a mean field functional. Okay? But I'm using it naively, like most people do, I think.
Exactly. Some other questions? Okay, if not, let's thank our speaker again.
Maybe I just make a short announcement. After
Do you on the microphone?
after the last speaker of the session, there is a planned tour of the campus, and I think it will be at 4:20, 4:30, and for those who would like to take the tour, the campus is really very nice, and you know, the guy will take you, the van will take you around the campus. Arnaldo Gamal will be your guide, this man. And he knows the campus very well, so he will just let you know what different places are really are. I mean, you know, the Institute for Biology, for whatever, chemistry, etc. And the idea is at 5:30, the van will come back here to pick up those who didn't take the tour and go to the hotel. Okay? Is that clear or? Yeah. Okay.
Okay, we were supposed to go to a coffee break. Maybe instead of 20 minutes, we could take 10 minutes, and because we're running a little late, or just relax. Okay. No, the second talk was supposed to start at 3? Oh, no, we are almost on time. Okay, yeah, now we are good. Enjoy your coffee. Hello. Oh, boy. Okay. You guys have no idea what we went through during the break, but the animations are running. Yes. All right, that's good. 10 seconds before I make a terrible announcement, here we are with the new with our next speaker. I need to practice my Japanese pronunciation. All right. Makoto Tatsubota.
Right.
Tsubota. Okay. So he's going to be talking about recent topics of quantum hydrodynamics and turbulence. You changed the topic, right? No. Oh, yeah. Okay.
Okay. What a relief movies work. So, first of all, I'd like to thank organizers for inviting me this wonderful conference. I'm Makoto Tsubota from Osaka City University. I'm talking about recent topics of quantum hydrodynamics and the turbulence. And first, I'd like to show you briefly discuss what is turbulence. What is quantum turbulence? The second topic is, I think this is a very important recent work on synthetic dissipation and cascade fluxes in turbulence. And the third topic is I'd like to discuss the multi-component BCs. And finally, I'd like to discuss important future problems of this field. So, what is turbulence? What is quantum turbulence? So, actually, surprisingly, the definition is not unique. So, if you look at the textbook of hydrodynamics, you can find different kinds of definition for turbulence. So the definition of the turbulence depends on the books, depends on the scientist. Well, something like that. So it's very surprising. But of course, you have some necessary condition of the turbulence. The velocity field should be disordered and unpredictable. But probably this is not enough. This is my opinion. My opinion, you may have a different opinion, but my opinion, the sufficient condition of the turbulence is the disordered physical variables obey some reproducible statistical law, such as Kolmogorov spectrum. So this is a famous story. In a fully developed turbulence, the energy spectrum, this is a definition of the energy spectrum, is known to show some statistical law. So this is a cartoon of the case. The horizontal axis refers to the wave number. The vertical axis refers to the energy spectrum. And in a statistical steady state, the energy is injected into some low wave number. And the injected energy is transferred from small k region to large k region without being dissipated. And this inertial range, the energy spectrum, shows the famous Kolmogorov -5/3 law. The energy transferred to the final dissipative range is dissipated by the viscosity in a usual viscous fluid. And this cascade process believed to be such kind of cascade process. This cascade process is called the Richardson cascade process. Namely, the injected into the large scale, and this is some sort of eddies or bolts, which are broken up to smaller ones similarly, and eventually being dissipated, disappears here. However, it's very surprising. Most textbooks of hydrodynamics describe such kind of cartoon, but this is only a cartoon. Nobody has ever confirmed it clearly, because it is not so easy to identify each eddy in a fluid. For example, this is a famous sketch of Leonardo da Vinci. This shows some sort of bolts, but it's not so easy to each eddy bolts in a classical fluid dynamics. Then, what is quantum turbulence? Quantum turbulence means turbulence in a quantum condensed fluids. And historically, the main stages of quantum turbulence are, one is the superfluid helium since 1950s. The other is atomic Bose-Einstein condensates, its discovery of 1995. So, quantized vortex is a vortex of inviscid superflow, and any rotational motion in a superfluid is sustained by quantized forces. Quantized forces has some characteristics completely different from the usual forces. First, the circulation is quantized by this quantum circulation. A vortex with a quantum number larger than 2 is unstable, so every vortex has exactly the same circulation. Secondly, this is a vortex of inviscid superflow, thus being free from the decay mechanism of the viscous diffusion of the vorticity. So our quantized vortex is very stable once it's nucleated. Thirdly, the vortex core size is very small, the order of the coherence length. In the superfluid helium-4, the core size is known to be the order of angstrom. Even in cold atoms, the core size is the order of the micrometers. So because of these reasons, our quantized vortex is very well defined and compared to the usual vortices classical fluid. So here we'd like to compare classical turbulence and quantum turbulence. This is my favorite movies. So here is a dragonfly, and you can find this is a visualization of a real fluid. And if you look at carefully, you can find some eddy or vortex-like structures behind the wings of the dragonfly. But these vortices are unstable and not easy to identify each vortex. So, of course, we can define circulation in the fluid, but the circulation differs from one to another and not conserved. On the contrary, our quantum turbulence consists of quantized vortices which are stable topological defects, and every vortex has exactly the same circulation, and the circulation is conserved. So we can say quantum turbulence may be much simpler than classical turbulence because each element of turbulence is well defined. So this is the advantage of studying quantum turbulence compared to the classical turbulence. So what happens to the quantum turbulence in atomic BCs? We can have various kinds of quantum turbulence. For example, we can control the dimensionality 3D or 2D, and we have a single component, multi-component BCs, including spin-orbit BCs, spin-orbit coupling, etc. And we have several providers of turbulence, vortices or wave, namely the body of excitations, or spin, or their mixture. So anyway, we can many kinds of turbulence in cold atoms. This is what we call the zoo of the turbulence. So what is most important problems in quantum when we study the quantum turbulence in cold atoms? So this is my opinion. We should answer what is turbulence and how to characterize the turbulence. So quantum turbulence of cold atoms, some advantages of classical turbulence. So as told you before, the elements of such as quantized vortices excitations are well defined, and we can control the geometry and the interaction, of course by using the Feshbach resonance. So I'm coming back to this page in the last of my talks, but please remember, what are the challenges of research of quantum turbulence? This is a Kolmogorov spectrum. This is a cascade process in the wave number space. But if we have such kind of structures, this is a real space cascade. And the connecting the wave numbers cascade and the real space cascade would be very interesting. It's impossible in a classical turbulence. Next, we are coming back to this part, in the last part, and finding the order parameters of the turbulence. Thirdly, investigating the transition from laminar to turbulence. Finally, we should consider crossover between 2D and three-dimensional turbulence. I'm coming back to this part in the last talk. So, after the realization of BC in cold atoms in 1995, most efforts were devoted to quantized vortices under a rotation. So this is our numerical simulation of the Gross-Pitaevsky model. And under the rotation, the cold atom BCs making some oscillation, and some vortices enter the surface, and eventually these guys form a vortex lattices. In this case, you can find the number of the vortices. In this case, 6 quantized vortices. And this scenario of the dynamics is very consistent with the famous observations by the Jean Darival's group, like this. But how to consider the quantum turbulence in cold atoms? So several methods were proposed by theorists. For example, the phase printing was proposed by Natasha Balfour and Boris Svisnov, and our group proposed manipulating the trapping potential, or Karol Barengis' group proposed starting the condensate. But I like this method very much, so I'd like to show you. So, first, our idea is making quantum turbulence by combining two rotations. First, we confine our cold atoms by a weakly elliptic potential like this. Here, the very small parameter epsilon and epsilon 2 shows a very small anisotropy of the system. Then, first we rotate the system around the x-axis, next around the z-axis by using these rotations. Actually, this idea was used by water in a classical turbulence by the Kyoto University group long time ago, 12 years ago. So this movie is very interesting. This is experiments. Can you find? Here is a sample cell, and water is confined in this sample cell. And this sample cell rotates around the horizontal axis. Then the whole apparatus on the rotating table. So this water is subject to the two rotations. It's quite interesting. And these scientists injected tracer particles into the fluid, and they found, in the case of rotation around one axis, as we expected, this fluid makes a solid body rotation. However, in the case of a rotation around the two axes, the fluid becomes turbulence. So it's quite interesting. And we used this idea to our cold atoms. So this is a numerical simulation, a gross model by the two rotations. And we calculate energy spectrum of the case. And this is a result. And in our case, the inertial range is not so wide because the lowest wave number corresponding to the, of course, Thomas family radius, and the highest wave number is corresponding to the coherence length. Usually the range is not so wide. But still, we obtained some power law like this. And the exponent is 1.78, which is different from 5/3. But it's okay, because our system is anisotropic because of these rotations. Originally, colomorph spectrum 5/3 was obtained for isotropic homogeneous turbulence. So our exponent may be different from 5/3. The point is, but we could find some power law. And probably partly motivated by our simulations, the boundary Bagnatos groups made excellent experiments. So the Brazilian San Carlos group, for the first time, succeeded in making the three-dimensional quantum turbulence in cold atoms by using the washing machine method, as Bandere told us yesterday. And after that, several groups succeeded in making quantum turbulence in two-dimensional cases. For example, this is a result of the Arizona Brian Anderson's group, and this is a result of the Shin's group in South Korea. And the several groups succeeded in making quantum turbulence, 3D and 2D case. So, I'd like to talk about these topics. Probably this work must be most important in the quantum turbulence in cold atoms in these few years. So Cambridge group succeeded in making a box potential, and they succeeded in making a turbulence in a BC trapped by a cylindrical box potential. And by the time of flight experiments, they observed the they showed the momentum distribution, showed some power law like this. Also, in this case, the range is not so wide, but they obtained some clear power law like this. And the next step, our groups make the collaboration with the Cambridge group, and this paper observed for the first time the cascade process in a turbulence by a very interesting method. So we excite the system by low wave number by pumping, and if the turbulent cascades propagates, actually by a very clever method, we could observe the cascade flux here. I will explain the detail. So, how to excite the turbulence in this case? The BC is trapped by a cylindrical box potential like this, And the system is excited by an oscillating potential along the x-axis. So the potential moving like this. Okay. Then, if the cascade propagates to the higher wave number, we can observe this cascade process by some clever method. So our basic idea is very simple. Originally, this is of course BCs. So all particles has a very, very lowest kinetic energy. So these guys are not allowed to escape from the potential because of the potential height, UD. However, if the kinetic energy of each particle exceeds this potential barrier, namely, if the wave number exceeds this critical value, these guys are allowed to escape from the potential. Is it possible or not? Not. Actually, it's possible. Because, so, if the cascade front propagates and exceeds the critical value, namely here the critical value, these particles can escape from the potential. So the Cambridge group observed the loss of the particles from the potential. I think it's a very, very clever method. And this is an experimental result, number of the lost particles. So Cambridge group changed the depth of the potential. So namely, change the potential. If the potential is deep, corresponding by using these relations, the critical wave number becomes to the higher wave number. So when the potential becomes deep, the onset of the loss is delayed and the loss rate becomes small. So actually, the Cambridge groups observed such kind of behavior. Could you understand what I mean? And also, these observed some scaling of the onset Ts as a function of the potential depth. So in order to confirm, yes, so if this picture is correct, we can say the energy cascade flux, something like that. Namely, the product of the loss rate and the kinetic energy of each particle. This should be the cascade flux. As far as I know, this is the first observation of the cascade flux by the quantum turbulence and the classical turbulence. I've never heard of such kind of story. So in order to confirm this picture, now we are making the simulation of the Gross-Pitaevsky model. This is a three-dimensional simulation, BC, in a cylindrical box potential. And every parameter is completely confined to tuned to the Cambridge experiments. So system is excited on this axis. And the first such kind of excitations appeared. Then gradually, through the nonlinear interaction between these modes, the system becomes to a turbulence like this. But this is still a wave turbulence, no vortices, no quantized vortices. Turbulence of a wave or Bogoliov excitations like this. So this is a similar story. But what happens? So this is also another Gross-Pitaevsky model simulation. Namely, in the early stages, something like that. So you can find very large structure. But in the late stages, the density waves, something like that. So you mean that this is very fine structure. So by the turbulence develops, this is a time development of the corresponding correlation functions. At the beginning, the correlation function has a peak in the low wave number, but the turbulence develops gradually, the cascade fronts propagates to the higher wave number. So this was, yes. So we make the simulation for the particle loss and the onset time, and there seems to be similar to the observations. But very, very recently, we focused on this anisotropy of turbulence. So this is another picture appearing in their Nature's papers. And by the time of flight experiments, they found how the turbulence becomes anisotropic, from changed to the anisotropic to isotropic. So this is the geometry of the case. First, the density, integral of the density along the x-axis, and they obtain the two-dimensional density. Then the two-dimensional density integrated by the radius between some R1 and R2. Then they define the anisotropic parameter A. If the completely the isotropic, this P theta should be 1 over 2 pi. So this parameter should be 0. But if this turbulence is anisotropic, this parameter becomes some finite. And the Cambridge group, by the time of flight experiments, they observed such kind of behavior. The horizontal axis refers to the excitation amplitude. The vertical axis refers to the anisotropic parameter like this. So the point is something like that. So the excitation is relatively small. The system is anisotropic. But if the excitation exceeds some critical value, the system becomes turbulent. But the Cambridge group, this is observations, but they don't know what happens. And in order to confirm, we continue the numerical simulation of the Gross-Pitaevsky model. So it's quite interesting. This is first of all, this is a relatively small excitations, weak excitations. So along the excitation like this, and the system becomes weakly turbulent, but still they keep some anisotropy. But in the case of very strong excitations, these guys, so by the strong excitation, this turbulence becomes isotropic at early times. So it's surprising. This is the dynamics of the Fourier component in both cases. So this is a Fourier component, and the central part corresponds to the BC, condensate. And in the relatively small excitation case, gradually, after these guys try to expand, but still keeps some anisotropy. But in the case of relatively high excitations, these guys expand fast and becomes isotropic like this. So this must be closely related with the observations by the Cambridge group. So this, yes. Yes, this is a density, density in the Fourier component, Fourier space. So yes, it's a quite interesting. Pardon? Yes, this one. So we calculate the anisotropic parameter, and this is our numerical results. So this is an observation of the Cambridge group, but they are not so good argument, but it's okay, because this observation was obtained by the time of flight experiments. But in our simulations, we keep the condensate trapping potential. So the situation is just different. But anyway, we have the qualitatively similar behavior, but of course we have to be more careful, and we investigate careful. So I'm going to the next topics. Yes, yes.
No isotropic part. You still observe the power law.
We haven't, in this calculation, we haven't yet calculated energy spectrum. Not yet. Well, of course we should do. But this result is very, very brand new. We obtained it 2 weeks ago. So we have not, of course, we should calculate the spectrum, but not yet. So I'm coming to the next, another topic, multi-component BCs. Depending on the symmetry, multi-component order parameters can yield various kinds of topological defects. For example, superfluid helium-3 or superconductivity with non-S-wave symmetry, etc. One of the important problems is, of course, what happens to the triangular abricos of lattice if we have multi-component BCs. So two-component BCs are well described by the coupled Gross-Podolsky equations. It's a well-known story, where G11 and G22 refers to the intra-component interaction, and G12 is the intercomponent interaction. And if the product of G11, G22 is larger than G12 squared, two BCs are like to be mixed. But on the other cases, two BCs are phase separated. This is a well-known story, which is described in the textbook. And this picture was appeared in the Arnold's presentation yesterday. And we obtained the equilibrium state of the vortex lattice structure of the two-component, rotating two-component BCs. This is a phase diagram. The point is, in these cases, we have a triangular lattices. Both components show the triangular lattices. But because of the interaction between two components, it's exciting. So the vortex core of one component is filled with the other component. So these triangular lattices just shifted. But if we change the parameter like this, this triangular lattices changed to a square lattices. Square lattices is not so trivial. And after our predictions, Girard's Eric Cornell's group observed the square lattices in the rotating two-component BCs. But still, this is a vortex lattice under a rotation. Then we are interested in the quantum turbulence in multi-component BCs. So multi-component, two-component BC is still described by this equation, coupled Gross-Podolsky equation. And we consider the case of the mixture is stable. However, the relative velocity of two components, namely the counterflow like this, should make it unstable. This was proposed theoretically by Yukav a long time ago, and after that, Peter Engel's group observed this instability. But we are interested in, we performed the three-dimensional two-component quantum turbulence. So we make the two components, make the counterflow of two-component BCs. What happens? So this is a red and blue line shows the quantized velocities of each component. So through some instabilities, these guys go to the binary quantum turbulence. So what happens actually? So I will explain the story. So the thing is, first solitons appears and the vortex loops appear, then leading to the quantum turbulence. I will explain the detail. So first, the unstable mode appears, and the unstable mode, which is describes solitons, and which is amplified to this shaped like low density regions. Then quantized velocities, namely the vortex rings, are nucleated inside the solitons, and next these velocities expand and grow. Then these velocities expand to reconnect with other velocities, and eventually the velocities become tangled like this. This is a story. So this part is very interesting. So we calculate the momentum exchange. Namely, originally these two BCs are superfluid. They have no viscosities, but this is a time development of the total momentum of each component. At the beginning, nothing happens. At the beginning, nothing is happening. They pass through each other. However, if the quantized velocities appear and the vortex line length density grows developing vortex tangle, then it's surprising that two species start to communicate through the quantized velocities. So the relative velocity reduced, and eventually they are stopped. So the point is that anyway, these two species, superfluid species, communicate through the quantized velocities. And this is a new kind of mutual friction between the two condensates, exchange momentum between them to reduce their relative motion. So such kind of experiments were actually performed. So this is Peter Engels group. They made a counter flow of two component species. And they observed dark, bright soliton trains like this. But they never observed the turbulence. Another experiments were performed by the Japanese group, and these guys also making the counterflow turbulence, counterflow of two component species. They obtained some instability, but they never observed the turbulence. But probably this is because of some spatial resolutions. I believe by making such kind of method, we can realize two component quantum turbulence. So I'm coming to the last topics, the dimension, manipulation of the dimension. So in the context of classical turbulence, the turbulence is known to depend strongly on the dimensionality. So this is a three-dimensional case. As I told you before, the energy is injected energy flows from small k to large k. However, in the two-dimensional cases, the story is different, which was predicted by a long time ago, Kreitzmann. And in the two-dimensional case, we have an inverse energy cascade. So the energy flows from large k to small k region. So I will show you some typical cases, typical simulation, quite interesting. Yes. So this is a two-dimensional Navier-Stokes equations, and yes. First, okay, quite interesting. So first, red and blue line show the sign of the vortices, okay? So at the beginning, upside and low side, positive and the negative vortices are confused. However, if the time develops, the two-dimensional case, the red and the blue vortices get together. Could you find? And we use the periodic boundary conditions. So eventually, the only giant red vortices and giant blue vortices survive. This is what we call the formation of the Onsaga vortices like this. So in the two-dimensional cases, we can have such kind of interesting behavior. Could you find? Finally, only one red vortex and one blue vortex survives. This is, of course, a result of the inverse energy cascade, and this is also the formation of a giant vortex. So, as I told you before, the story is completely different from the two-dimensional and the three-dimensional case. So why not study the dimensional effect in cold atoms? So formation of Onsaga vortices, giant vortices, simulation to the Navier-Stokes equation I showed you before. And this topic is studied by several groups now. This is Chris Helmersson's groups, and they study the Onsaga vortice formation in a single component species. So, for example, this is the typical cases, and here is a positive giant vortex, here is a negative giant vortex, and eventually the single component species. Even if we started from the random quantized vortices, these guys get together and forming a large Onsaga vortices. Then, very recently, we studied this problem by the two-component basis. So story is just different. So the forces of two components are phase separated depending on the parameters. So this is a typical cases. So this is a BC1 and this is a BC2. So typical case is something like that. BC1, the forces occupy this region, but the forces of BC2 occupies another region, and they are phase separated because of the interaction between the forces in different components. So this is a phase diagram we obtained in the two-component cases. In these regions, the condensates are phase separated, as you know. And these cases, in these regions, the condensates are miscible. However, the forces in this case, we obtain the critical value about 0.6. If in these regions, the two components form Onsaga forces independently. But here, in these regions, because of the strong interaction between the forces in different components, these forces are phase separated. So probably by the experiments we can, I believe such kind of behavior should be observed. So finally, let me briefly discuss what are the challenge of the research of quantum turbulence. So as I told you before, the most important question is what is turbulence and how to characterize the turbulence. We should attack this problem. So as I told you before, first, connecting the wave number space and the real space cascade, it's very important. And this approach is impossible in a classical turbulence. Next topic is finding the order parameter of the turbulence. So let's consider, for example, we have some arbitrary configuration of disordered forces. But do you think all disordered forces belong to quantum turbulence or not? Probably no. So the quantum turbulence is a narrow region compared to the such kind of disordered set of the disordered forces. So we have to define the quantum turbulence by using for example, the statistical law like the Kolmogorov spectrum or introducing order parameter. But I have no ideas. Next is let's consider the transition from laminar to turbulence. Recently, I heard that, for example, boundary Walnut groups try to make the turbulence by using this two rotation methods. Okay, this is a phase diagram. So if we rotate the system along the z-axis, as you know, we find the average cost of lattice appears along the z-axis. Then if we rotate the system along the x-axis, the average cost of lattice appears along the x-axis. Then if we combine the two rotations, we obtain such kind of behavior, vortex tangle. Then it's quite interesting. So if we prepare this state and if we increase another rotations, this average cost of lattice should melt, change it to a vortex tangle. But nobody knows what happens here. So for example, it would be very interesting to observe such kind of behavior. Nobody has ever considered the problem theoretically, numerically, experimentally. So I think it's a very challenging. So of course, another important topic is, of course, this is a crossover between 2D and 3-dimensional turbulence. Our advantage of cold atoms is we can change the dimensionality like this. So by changing the trapping potential from 2D to 3D, what happens? So in the 3D cases, the energy flux flows from small k to large k. 2D cases, energy flux flows from large k to small k. So there must be some crossover between them. We don't know what happens. Nobody has ever considered this problem experimentally, theoretically, and numerically. I think this is also another very, very important topic. So, okay. let me summarize my talk. So I discussed these topics. Thank you very much for your attention.
Will we have time for a few questions?
Yes.
I can't speak loud enough, I guess. So, Tsubota, I'm going to start from the end. Do you believe that if we find a way to suppress reconnection
Suppress reconnection?
in 3D, the system will go in a inverse cascade?
Yes.
You think so?
You mean...
I'm not saying that I know how to suppress
You're talking about the two-dimensional case,
a 3D.
3D. Yes.
Because you want to go from 3D to 2D, right?
Yes.
And see the reversing of the energy flow.
Yes.
Okay. What my question is,
Yes.
if I find a way like massive vortices, I trap another atoms in the vortex or something.
Yes.
I suppress the reconnection.
Yes.
Do you think that will reverse? I will have an inverse cascade?
Yes. In order to make the three-dimensional vortex tangle, of course, we need lots of vortex reconnections. If we have some two-dimensional or anisotropic turbulence, anisotropic vortex lattices, it has a very less reconnections. So the point is, yes, I think so. I agree with you. Yeah.
Okay.
In principle, it's possible. Yeah.
So maybe we can, instead of changing the dimensionality, change the mechanism, right?
Yes.
So that will be
Yes, I think
equivalent.
so.
And maybe
I believe so.
the things will be easier.
Yeah.
The second question is, what you think is the big advantage to have a homogeneous system if I have that big rigid wall that somehow makes the system not homogeneous at all? If I have a soft wall,
Yes.
so why, I want you to tell me what is the advantage to shift to box potential. If I have that rigid wall, you
Yes.
think it's an advantage, or there are things that's only related to the rigid wall present?
Yes. The advantage of a box potential is the condensate is almost uniform.
Yeah, but we have a big rigid wall.
Yes. Anyway, uniform condensates is easy to analyze. And yes.
But this is the debate I want to carry on with you. I mean, having a density that goes softly down
Yeah.
instead of a density that comes abruptly down.
Yes.
So
of course, probably I think that this is not essential difference.
no. Thank you.
Yeah.
It's
But,
because a box, the states in a box in a larger region, you're going to have a more homogeneous.
Yes,
Because
yes.
if you have a harmonic trap, it's going to be inhomogeneous everywhere.
Right. Right.
Right. But in the box, at least outside the edge.
Tell me if the effect you see is just due to the abrupt
Sure. Yeah.
the density, or it is something else.
Sure. Yeah.
Yeah.
Yeah. I agree. I mean, you can do a fully homogeneous calculation,
Yes.
right? But
Yeah.
realize that. So you might be able to answer this question if the effects that they see is really because of this border effects or it's coming.
Yes. Of course, in our cases, by using the box potential, the cold atoms just penetrated through the walls.
Mm-hmm.
So this is probably not essential problems, but this is some advantage of using the box potential.
Okay. Chris?
Yeah, I had a couple of questions. Yes. One is, at one point I think you had GP simulation from 2 precessions.
Yes.
And you got an exponent 1.78.
Yes.
Plus or minus 0.194 you quoted, and you expressed surprise it wasn't 5/3.
Yes.
But that is 5/3 within the error bar. So I don't understand
Yes.
your comment.
Actually, in this, yes, I'm coming back to this part.
1.7 is very close to.
Yes, your question is very important. Yeah, I know. Yes, you're talking about this part.
Exactly.
Yes. As I told you before, originally 5/3 exponents were obtained for isotropic homogeneous turbulence. But our case is not isotropic because of the two rotations. And after this work, actually, we performed the numerical simulation of the three rotations. And the made a similar calculation, but using the three rotations. Three rotations make the turbulence more isotropic. Then the exponent is get closer to the 5/3. So if make the system more isotropic, the exponent approaches 5/3. But I don't know why it's different from. But anyway, anisotropic cases, the exponent may be different from 5/3.
Right, but in this case, it is 5/3 within error bar.
I don't think it's error bar.
1.66
Yes,
is within the error bar.
Yes, but the average is 1.78. But I'm not quite sure.
Okay.
Yeah.
Theoretical point of view is not exactly the same.
No. Yeah.
Yeah. Oh, okay. The other question I had was you mentioned that when you had this tangle of circulating vortices that each had one quantum. They were all the same
Yes.
amount of circulation.
Yes.
Why do you never see like two quanta?
Two quantities. Yes,
Is
it's
it
important.
unstable or something?
It's important questions. So, quantum, the quantized vortices with a quantum number larger than 2 is unstable. So,
They always break into
yes, of course we can prepare the such kind of high quantum number vortices by, for example, phase manipulating. But we know these guys are unstable, split to the each quantum vortices.
Is that because it's in 3D? Because later you got these giant vortices.
So the energy of a high circulation goes to L squared.
Yes.
If you have a
That-
equals 2 circulation, you have 4 times more energy. So if you add the 2 vortices, you have a balance of factor of 2 with the energy. So it's unstable. It decays in 2 of circulation 1. You understand? Because
Yeah.
the energy goes with L squared, right?
Yeah, that's a story. Yeah.
I see. That's a nice argument. But then why do you see the giant vortices? Is
Yes,
that because it's
this
2D?
This is 2D cases.
Okay.
The giant inverse energy cascade is caused by the conservations of the entropy. So in a case, two-dimensional cases, we have, of course, high Reynolds numbers. The entropy is also conserved as well as the energies. So this is an important point for the inverse energy cascade. Yeah.
Yeah, towards the end of your talk, you wrote down a few open questions, and
Yeah.
one of them was how to characterize turbulence.
Yes,
Is that still a completely open question?
I think so. I think so.
Because you show like this momentum distribution, which has this k to the 5/3
Yes.
power. Is that not a signature of quantum turbulence?
Yes, of course. If you find some such kind of power law, I think it's an important signature of turbulence.
Mm-hmm.
Yes. But this is a case of a fully developed turbulence.
Okay.
Yeah.
So can you turn back to that slide? I think it was maybe the third one from the end.
You're talking about the last part. This one.
Yeah, what is turbulence and how to characterize turbulence? So is it one of these things that you know it when you see it kind of a thing? I mean, is there really no definitive quantitative characterization of turbulence?
Yeah, I try to find, but nobody knows probably. Yeah. So this is, of course, depends on the definition of the turbulence. And we try to find some signature of the turbulence or the other parameter of the turbulence, but probably no general agreement of these topics.
Yeah. But, well, like the third point here on your list, investigating the transition from laminar flow to turbulence.
Yes.
If you don't know what turbulence is, how do you know that you've got it? So you can follow this transition. I could see how, you know, you were talking about shaking along one axis,
yes,
it's laminar, shake along the other axis,
yes.
it's laminar. And then in between, there's presumably turbulence, but how do you define what that boundary of those lines?
Yeah, I don't know what happens here, but anyway.
In classical fluids,
Yes.
people don't know also how to define in a very precise way. They rely on empirical quantities like Reynolds number.
Right, right.
So I think in turbulence, people need other quantities, the way you say, to really see variation.
Yeah.
In the flow, you see a suddenly drop of pressure. When you go from laminar flow to turbulent flow, there is a drop of, right? I think it's...
So
Yes.
could you measure compressibility then, for example?
Yes. Yeah.
So you expect there to be a sharp, is that a phase transition? Is there?
I don't know. I don't know. It's an important question. What happens?
Yeah.
This is probably the related to the instability of the vortex lattices. If we including such kind of rotation, this problem is related to the instability of the vortex lattices. But I don't know what happens here. I don't know. This is a phase transition or crossover. I don't know.
Yeah, very interesting.
Yes, nobody knows.
Question? Anyone else has a question? Or else I'm going to give to Vanderlei again. Oh.
I'd like to understand better the inverse cascade, because you showed Navier-Stokes and you didn't show Gross-Pitaevsky, or you show it and I didn't understand this reverse in the 2D case. Can you explain another time, please?
Yes.
How it's going back?
Yes. Actually, your point is very important, and namely,
there is no movie on
yes.
Gross-Pitaevsky, or there
Yes.
is. I didn't notice.
Actually, in the case of quantum fluid and the two-dimensional Gross-Pitaevsky models, whether we have an inverse energy cascade or not, I think this problem is still controversial. Yes. And because, as I told you before, the conservation of entropy is very, very important. Entropy is some sort of a total circulation. But in the Gross-Pitaevsky model, you know the positive and negative forces make the pair annihilations. So the entropy is not necessarily conserved. So some authors says this must be occurred, but some authors no. So I think whether the inverse energy cascade occurs actually in a two-dimensional quantum turbulence is not still I think controversial.
But you cannot check it numerically if it's happening.
Yes, we did, and some groups did, but not so definite answers, in my opinion. Okay. It's still a controversial problem.
I thought that the simulation by the group of Australia.
Yes, Chris Hermanson's group.
In the simulation, they
Yes.
saw the separation of vortices and
Yes.
anti-vortices quite clear.
Yes.
No? I mean, but I agree with you. Still, people never saw what you can see in the classical simulation, right?
No.
Tsubota, let me ask you another question.
Yes.
When there is reconnection, there is a lot of sound waves.
Pardon?
When there is reconnection,
Yes.
there is a lot of sound wave
Yes,
produced.
lots of, exactly. In the case of Grosseteste model, when the vortices make reconnections, sound waves are excited from the reconnecting point. Yes,
So-
it's true.
Yeah, and do you take that in account when you try to solve and get the power law type?
Uh-huh.
Because this is a very disturbing thing in the system that
Yes,
I want to know if that's in the calculation.
You're right. Grosseteste model describes the compressive fluid. So when we consider the energy spectrum, we have to divide the compressive kinetic energy and incompressive kinetic energy. And if we consider the energy spectrum, something like that, we should focus on the only the incompressive kinetic energy.
Okay. Okay. If there's no more questions, let's thanks again our speakers.
Thank you very much.
And the speakers for today's section.